So you guys, I'm going to make it official. If I have a differential equation that I can express in this form, I will subclassify it as a linear nth order differential equation that's non-homogeneous. It's non-homogeneous because I've got a forcing function f over here. I'm assuming it's non-zero. If, however, that function f of x on the outside is indeed equal to 0, then I will subclassify this as an nth order linear homogeneous differential equation. So homogeneous simply means I've got a 0 function over there. I know I'm going to slip up on my words. I might as well give you the name. I typically refer to it as my forcing function. And we need to start talking about techniques for solving higher order differential equations.
Why is your first y to the n not have a constant?
It just makes it convenient for me usually, not always, but usually. And even if I did have a constant out there, I shouldn't call it constant. If there is a coefficient out there, call it a sub naught of x. If I divide both sides by it, that's what I get. That's why it doesn't matter. By the way, did you guys notice that the a1 of x, a2 of x, all the a sub n of x, they're functions in x. And I don't care what those functions are, I will still subclassify this e as linear because it's linear in terms of y and y's derivatives. It has nothing to do with the coefficients. As a matter of fact, if you want, you can even give a name for all those coefficients. Taking a peek at the differentiation process, I'm going to start changing my notation. Okay, you guys check this out. Given a function y and x. To differentiate, here's a notation I'll be using. I'm going to use my uppercase D, and I'm going to act on my function y. When I do that, I'm simply referring to the first order derivative for y. Now, sometimes, if it's not clear what the independent variable is, sometimes you'll see the notation with subscripts, big D sub x, just so you, the reader, understand that I'm treating y as a function of x, and I'm differentiating with respect to the variable x. However, if I were to differentiate twice, that's the action I take. As a matter of fact, to differentiate n times on y simply means I'm differentiating on the n minus 1 derivative acting on y. So that's how I'm going to treat higher order derivatives. As a matter of fact, I suppose I can even rewrite this equation. I'm differentially operating n times plus a sub 1 of x times differentially operating y n minus 1 times. All the way down to differentially operating on y once with a coefficient. And then maybe even not at all. And so I think another way to write the entire left-hand side is I've got this rather complex differential operator acting on y. Now, as you are going to see, it's going to be a lot easier to solve a DE that's homogeneous as opposed to non-homogeneous. Chris?
Can you really distribute operators like that?
Absolutely, because I think the differential operator is actually just like a linear transformation. I think it distributes over addition as well as scalar multiplication. After all, if you and I were to differentiate maybe an x squared plus y, isn't that the same thing as differentiating x twice? And adding to that differentially operating on y. And again, even constants get pulled out of the differentiation process.
Well, it's different than your d is outside parentheses. In this case, it's within the brackets, but I guess it kind of makes sense.
You know what's kind of nice about this notation? You can almost think of this as multiplication. In fact, they behave just like polynomial expressions. You know, what's else is really slick is that if I just simply call this thing right here L, then I think rewriting this differential equation can be written as concisely. A linear differential operator acting on y is nothing more than f of x. What would this represent in words? Anybody? I'm just shaking guys up with the notation.
Where I guess L of y is equal to 0, not f of x.
Nice. So I think the kernel of this transformation of this differential operator, this polynomial differential operator, is being sent to the 0 element. In other words, I think we're dealing with the solutions to the corresponding homogeneous DE. I agree. Again, it's
sure
a really
what
goofy
you
question, I'm just
want
shaking you up
us
so you can understand
to
the
do.
limitations. Michael?
Would that be like, it would split up into d squared y plus x squared y?
And what does that give you?
I'm not really sure. I think that's not.
How about the second derivative of y? Plus x squared times y?
Can you explain that?
Yes. All I'm really saying is I'm creating this more complex differential operator, and to operate on y, I'm simply, number one, going to distribute the y in the multiplication over the addition. I
So
can
you-
treat that as multiplication.
You're actually referring to your D as your differential operator, so,
I am.
okay, I see what you're doing.
And so I'm just being silly with my notation. I'm just asking it in a different way, can we differentiate with respect to y, with respect to x, twice?
Okay.
And I did. I know these aren't very useful questions. I'll get better in a moment. Well, you guys using my notation, notice how D1 operating on D2, operating on Y is nothing more than, well, this D1 operating on this D2 operating on Y. And to apply this differential operator on Y, isn't that just simply going to give me y prime plus 2y? But now acting on that function with this differential operator, let's see what we generate. Is that going to give me, is that a y double prime? Plus 2y prime. Plus x times y prime. Plus 2 times xy. Or shall I say, I've got a y double prime plus, how about x plus 2 times y prime, and then plus a 2 times x times y. And if I were to travel in the opposite direction, Chris? Say, for example, you're composing these two differential operators, but in a different direction, the other direction, I should say. I think D2, acting on D1, acting on Y, is going to be nothing more than my D plus 2 acting on my D plus X, acting on the Y. And that's going to give me D plus 2 acting on the following. Isn't that just going to be a Y prime plus XY? But now I got to slow down. Because now I've got my differential operator D acting on Y prime. I'll show more steps this time around. Plus my differential operator acting on X times Y. That's going to require the product rule. Plus 2Y prime plus 2Y. And now diving in, differentiating where appropriate. I think I've got a Y double prime plus, is that an XY prime plus Y? Plus my 2y prime, plus 2y. However, that's going to leave me with my y double prime plus something times y prime, namely, is that an x plus 2? Is that going to be plus a 3y? You guys just double check my arithmetic. Oh, shoot, check that out. These two answers, they're not the same. So when it comes to these differential operators, we do not have commutativity. Order is important. Now I gotta confess, if my L ends up being the product of two polynomial differential operators, in other words, merely polynomials in D, in other words, none of this X stuff, then I've got commutativity.
Just have a question on this last one, the third line. Where did the 2y at the end come from?
I think it came from a mistake. Yeah, you guys, what should this term be right here? Yeah, I missed my factor of x, didn't I? My apologies. It's gonna change my answer though, isn't it? That means my my coefficient for y ends up being, is that a 1 plus 2x? My apologies, thank you. But again, clearly not the same as what I had before in the other direction. Chris?
Is it associative?
When it comes to just polynomial differential operators, absolutely.
What about differential operators with an accent?
Unfortunately not. Associativity does not work.
And can you multiply two differential operators together?
Can I multiply two different?
Operators together?
You know, in a sense, I treat this as multiplication and composition. I think they're the same when it comes to differential operators.
But if you carried that multiplication slash composition out, would you get d squared plus 2xd plus 2d? Is it a legal operation?
Unfortunately not, because you would, in this case, not be differentiating a product. You decided that. So if these are nice, clean polynomials indeed, then things work out really, really nice. And for a while, they are going to be really clean like that. Okay, everybody, I'm going to start off by looking at a homogeneous differential equation. If you guys don't mind, I'm going to restrict my attention for a moment to just the second order DE. Notice how I do not have A1x, A2x, I just have A1 and A2. I'm trying to apply to you, the reader, that those coefficients really are merely constants. And I want to talk about solving this differential equation. Because if my solution is going to look like this, then check out what happens when I pick this up off the board. Slap it for y in those three different positions. It's not going to generate this.
Huh?
Do you guys not agree?
No.
Oh, you don't? What do they do?
Wait.
Yeah, I'll wait.
No, never mind. I agree.
By the way, each and every one of those three terms on the left-hand side has a common factor of e to the rx. I'll pull it out. And I don't care what r is. What can you possibly say about that factor right there?
What can we say about it?
Yeah, just panic and say something.
It can't be equal to 0.
It's definitely not equal to 0, so I can divide both sides by it. And I have r2 or r squared plus a1r plus ac2 is simply going to be equal to 0. Shoot, look what that is. That's a math issue. That's just a polynomial, or excuse me, in this case, just a quadratic equation. Will it always yield solutions? I asked, will it always yield solutions?
Not necessarily real ones.
Well, I think it always will. It's just that some might be complex. I might have complex solutions, but I always have solutions. Actually, what are my choices? I guess they both could be real numbers, or maybe I just have one real solution, or maybe I have two non-real complex solutions. I think those are the only three options I have. And I maintain if both these solutions are real, I have just solved my differential equation. Because I can solve for the r values. I know what they are. Matter of fact, this is so important, can I give it a name? I refer to this as my characteristic polynomial. Sometimes I refer to the entire equation, my characteristic equation.
So is that how you would write your answers, or would you?
Oh no, I'm just simply up in front of the board saying, hey, I can solve that equation. I've got solutions. Can I give you a quick example?
Sure.
Chris?
We're going to use the word characteristic a lot in this class.
Yeah. You open another book, some authors refer to it as an auxiliary equation. Same thing. You guys, this is a piece of cake. It's the first day in class, I'm solving such a DE, so I'm putting a little bit too much on the board. Personally, I would have just written down the solutions. But I think two solutions are going to be the following. If I take my characteristic equation, use my math D skills to solve that equation, I certainly find that r is equal to -2 or r is equal to +3. Therefore, we have two linearly independent solutions, namely this one solution, y1 of x, being equal to e to the -2x, and y sub 2 of x being equal to e to the +3x. Matter of fact, you can check me real quick to see if these really are linearly independent solutions. All you check is a Wronskian, and I just did. And the Wronskian's not 0. And I maintain that all my solutions can be formed by, gosh, you guys, I forget. We now have Math 31, we now have linear algebra under our belt. All solutions are going to be described by the linear combination of these two linearly independent solutions. So I think all my solutions are going to be in the form C1 times the first one plus C2 times the second. And if you don't believe me, how would you check me? How would you check me to see if I made a correct statement that all those solutions can make DE? Yeah, you just put it back in. Pick that function up off the ink board, slap it in for y once, twice, thrice, and see what you get. You'll get 0. You can double check that. But you guys, I'm nervous. My example's too
Easy.
yeah, it's too easy because technically speaking, I already had two solutions to the characteristic equation, and therefore that generated two linearly independent solutions. What if I saw the characteristic equation, I only came up with one solution? Well, since this is second order DE, I think I will always have two linearly independent solutions that generate the entire solution set. So when I only have one solution, that's going to be a problem. So as of now on the clock, I'm breaking this up into cases. Case 1. When it comes to this characteristic equation right here, if I have two unique solutions for R, then I know what my solutions to B are going to be. Actually, let me formalize this. If this equation right here has two distinct real solutions, R1 and R2, then all solutions to that second order differential equation are going to be the following, namely, linear combination of e to the r1x and e to the r2x. Piece of cake scenario. However, if it's the case that this characteristic equation has only one real solution, then all solutions are going to be in the following form. You guys, I don't want to bore you to death. I don't want to just slap it on the board. That would be unfair. So I want to prove to you that what I'm going to say is true.
So is this an actual theorem, or is this just rules?
Oh my gosh, you treat this as a theorem, you're going to be using every single day in class.
Yeah.
It'll be that important.
Is there a name?
No, it's just so important, I don't give a name to it at all.
It's just
It's how I differentiate
the important
my
theorem?
second order. Yeah, the big deal theorem.
The big deal theorem of differentiation?
No, I like to title something else in this class a big deal theorem. We'll say it
Okay.
at the end.
Can't see it on the camera.
What's that?
Trying to take a picture of it, I can't see it on the camera.
Oh, because it's so light?
It's blue, yeah.
I apologize.
Yeah, the light has got a glare on the
My apologies.
There we go. I got it.
You got it?
So you guys, if this characteristic equation right here has only one solution, say R equals R1, then doesn't that really mean that that particular equation looks like this? I'm just speaking math D language. Or shall I expand? But take a look at these two equations. Look what I'm circling in green. The coefficients for R. Don't they have to be equal to each other? Do you guys agree? Or shall I say, R1 could be interpreted as negative 1/2 A1. And what I want you to do next, I think, is an important deal. What I want to do next is, I want to find a second linearly independent solution to my DE. Because if I can find a second linearly independent solution to my differential equation, what it really means is that all solutions are going to be expressed as a linear combination of the two that I have. But I have to create my second solution out of thin air. This is a technique for solving a DE that you've not seen before. I've got a name for it. I call it reduction of order technique. And I really don't know why the author chose to discuss this technique later in this particular chapter, because I think I need it right away. And here is the reduction order technique for solving differential equations. It only works so if you've already got one solution. And I do. No. I think y being equal to e to the r1x is a solution to my DE. Unless you and I allow y being equal to u times e to the r1x to be another. And we will find what that function you have to do about it. So you guys, here I go. I'm merely going to pick this beast up off the ink board, slap it into my differential equation. Well, you guys, here's my differential equation over here. And so slapping in, is that going to give me the second derivative for this beast? Is that an A1 times the derivative of this beast? Plus my A2 times this beast. And if you guys don't mind, I'm just going to tackle the issue of differentiating where appropriate. To differentiate once, I guess it gives me the first times the derivative of the second. Plus the second times the derivative of the first. I'll split it. Yes.
I thought u was just another constant.
And if I said that, I misspoke. I want you to represent a function in x. So treat u as a dependent variable on x. And x is my independent variable.
So shouldn't it be u of x?
You know, I could write as u of x, and I think that would make it more clear. Plus, differentiating this, would that give me the first times the second? Plus the derivative of the first times the second. Oh, and I've got the lingering plus a sub 2u e to the r1x. Well, I guess I do have to dive in and differentiate one more time. Oh, shoot, that means a product rule a couple times. Okay, here goes. I got the first times the derivative of the second. Plus the derivative of the first times the second as is. And here too, differentiating this product, I guess it gives me the first times the derivative of the second. Plus the derivative of the first times the second as is. oh, I've got these lingering free terms, don't I? Plus A1 R1 U E R1x plus A1 U prime E R1x and plus A2 U E R1x. And all of this is set equal to 0. By the way, you guys, if I look at my previous line, did I forget to say that I've got an equation? And in collecting my terms, everybody check out what happens when I collect all the U terms. Expect U terms. I think I get this. Actually, I can't see them, you guys. Here's a single U term. Here is a second U term, and here's a third U term. Does that give me, collectively speaking, R1 squared plus A1R sub 1 plus an A sub 2? And if you now allow me to dive in and collect all the U prime terms. Actually, I don't know where they are. Here's one of them. Here's a second one. Is that it? Nope, I missed one. Here's a third one. And the coefficients there end up being R1, or 2R1, plus A sub 1. And then finally, there's only one single term in here that involves a U double prime. Here it is. I don't know, you guys, anything jump out at you with that equation? Anybody? Oh, really? Nobody? You can't take a peek at that equation and say something about the...
Well, they have a common factor, either the R1X.
Oh, you're right, divide both sides by either R1X is gone.
Okay.
What do you think we can say about that? Has to be 0, because I was assuming R1 was the solution to my characteristic equation. What can we say about this?
0.
Why?
Because it's a derivative of that. 0.
Because R1 is negative 1/2 of A1. And so I think in this differential equation, the only thing remaining standing is the following. I think it's just that last line, which means U's second derivative is going to be equal to 0, which means U's first derivative is nothing more than a constant, which means U's 0th derivative is just going to be the constant times x plus another constant. And shoot, I was trying to generate a second linearly independent solution, where the original solution, the first solution, is circle right here in red. But if my second solution looks like this right here, and if I choose C to be 0, K any constant, is that going to be linearly independent from that? If I choose C to be 0 and K to be 1, what's that solution going to look like?
The scale it has.
Yeah, it's just going to be the same solution I had before. Or if K is any number, it's the scalar multiple of the first solution. Therefore, I would not get a linearly independent collection of solutions, would I? However, you guys check out what would happen if I allowed K to be 0 and C to be 1. That means my U function is just x. Pick it up the board. Slap it in right here. I think another solution to make the E will be x times e to the R1x. And clearly, x e to the R1x is linearly independent from just e to the R1x. That being the case, it took a while, but I just described for you what all these solutions are going to look like. My solutions are going to be in the form where I've got a linear combination of my two linearly independent solutions. One of which was this. The other of which was this. Chris?
Are they necessarily linearly?
Yeah. One is certainly not a multiple of the other. Because to say that one's a multiple of the other means that one's a multiple of the other for all values of x. Wow, that was a mouthful. You guys got to be honest with me on this one. Because I don't know how you guys are raised mathematically speaking. We're all coming from different places. Do you guys know that this is true? Be honest.
you explain that?
Spoilers, I've never used it.
Bradley.
Nobody's
I knew who your
nobody's
math
showed me
31
this.
friend
Huh? You didn't show. Did
Yeah,
you
we-
show me
we-
this
no, we-
in math
I
31?
can never teach math 31 without
I've,
practice.
I've got it in my
Okay.
notes.
It looks somewhat familiar, I know in like electrical engineering, we often use cosine and sine data to describe AC current. We usually treat the cosine version as the real stuff. And
I don't
the
remember that
sine
in the
is
summer. You taught that in the summer?
So can I get a little mini math 31 lecture? Because you know what I've done so far? I've talked about solutions to these homogeneous DEs, but only when the characteristic equation gave two real solutions or a single real solution. Then I know the solutions to the corresponding DE. So, here too, be honest. Do you believe this is true? Everybody?
Lots of Taylor's pancakes.
Or listening to some with summation notation. You know, summation notation. Well, -1 to some power, we'll think about that in a minute. All over
N factorial.
to, I change it to an N, it looks nice. Two N? And now we'll raise a -1 to the.
Nth power.
Yeah, I agree. Does anybody else agree? And of course, you can think of the sign likewise as nothing more than one, excuse me, I misspoke, my apologies. I meant x minus 1/3 factorial x cubed plus 1/5 or 1/5 factorial x to the 5th. Or again, using your summation notation.
Two N factorial.
2n
Quantity factorial.
plus 1 factorial x to the.
2N plus 1.
Now we just need to figure out the power to which -1's being raised. Does this work?
That was me,
Are you happy?
no,
Oh, why not?
it should be N plus 1.
Oh, should it? Because I think when n is 0, I get an x term. And that should be a positive x. And so I knew this worked. You can double check my arithmetic. Do you guys remember this one? Jeepers.
1 plus x plus 1.
2 factorial plus x cubed and 3 factorial plus
Is that looking familiar?
Yes.
But you guys, I'm a mathematician. I can prove to you that what I'm saying is true. I can derive those power series out of thin air if you want me to. I'll do whatever you like.
Sure.
You said yes?
Do you want to just derive them out of thin air really fast for us? It's been a few months, so I'm a little rusty. I don't
You
feel
guys,
it
relax,
gets pretty
keep your
heavy.
feet up, and just let me know if I'm saying something that's not clear. If I've got a function f that does have a power series, in other words, if f can be expressed this way, then I think necessarily, in expanded form, the output of my function is c sub naught plus c sub 1x plus c sub 2x squared plus c sub 3x cubed. What I'm going to do is I'm going to show you what these coefficients, these c sub i's, really should look like. If I were to differentiate, wouldn't I get this? I were to differentiate a second time. Oh shoot, you guys, piece of cake. My second derivative is just 2c2 plus 3 times 2c3x plus 4 times 3 times c4x squared, etc., etc., etc. And I even maintain this third derivative function. Ev added x is simply a 3 times 2 times c3 plus 4 times 3 times 2 times c4x. You guys, I'm too tired. Can I stop? Let's take these individual functions and evaluate them. That's 0. I think I get this. I think I get this. I think f double prime of added 0 is going to be 2c2. I think nth derivative of f, excuse me, I meant the third derivative, my goodness. Ev added 0 is simply going to be 3 times 2 times c sub 3. Don't you guys agree that the nth order derivative, Ev added x equals 0, is simply going to be n factorial times c sub n? That being the case, I think my function, bless you, has a power series expansion, that these coefficients of c sub n are going to be nothing more than the nth order derivative for f, Ev added 0, all over n factorial times x to the n. That being the case, Brad, to show you that, oh, I don't know, for example, e to the x really has this power series expansion. I think all I have to do is proclaim that the output of my function is going to look like this. And if I allow f of x to be e to the x, oh, piece of cake, you guys, look at f prime of x. Look at f double prime of x. And look at the nth order derivative for f at x. But doesn't that necessarily imply that f is 0? F prime is 0. All the way down to the nth order for f, evaluated at 0, aren't they all simply going to give me values of
1.
Well, that being the case, if e to the x has a power series expansion, then I guess it's going to look like a c sub 1. Excuse me, I misspoke, didn't I? I meant c sub naught. But that's just a 1 over my n factorial. Where n is equal to, did I say 0 or 1? You guys, did I just flip that up? If n is equal to 0, I get the 0th derivative, that's just the original function. Ev added 0, but that's just simply positive 1. All over 0 factorial times x to 0 power, there's my first term. My second term just simply has a numerous position of the first derivative out of 0, but that's just a 1 again. And that's going to give me my 1 over 1 factorial times x to the first, plus my 1 over 2 factorial x to the second. So now do you believe me that e to the x, the natural exponential function, does indeed have this as its Taylor series expansion? Actually, I just keep saying Taylor. I really should be saying Maclaurin because it's centered about x equals 0. You know what, you guys? That was too much fun. Let me see that again. I maintain e to the x looks like this. So if I asked you guys to consider e to the, how much is I theta? Isn't it going to be exactly what I have up here? It's just that I'm replacing x with I theta. I think that gives me 1 plus x.
Okay, I remember this now. Yeah.
Okay, it is coming back. 1 over 2 factorial times I theta twice plus 1 over 3 factorial times I theta twice. I can just do one more. Now, if you guys allow me to just collect, how about this term? Then this one. Then this one. In other words, allow me to collect all the terms involving I to an even power. I'll rewrite them. I think that gives me 1 plus, actually, this is both. 1, check this out. It's a nice squared. That's just
-1.
But here, I to the fourth is
Same thing, -1.
times itself twice as positive
Yep.
1. Now, if you guys allow me to recollect all the other terms involving theta to an odd power, the very first one's I. I pull it out. And here's what's left over. But from the next term, I've got a factor of I cubed, and I cubed the same thing as
Did you just leave out your I theta?
what was that?
Did you just leave out your I theta?
Where?
Oh no, you.
So when I took the first
Okay,
term,
no, I see, I see.
I just pulled out the factor of I.
Okay. Okay.
But you know, with this one, I mean, if I pull out an I, there's an I